Hi, I'm Doug Black, editor-in-chief of Inside HPC. And today we're talking with a member of the Dell Technologies HPC community. He's Luke Wilson, Chief Data Scientist in Dell Technologies HPC and AI Innovation Lab. Luke, it's great to be with you today. Thanks for joining us.
Thanks for having me on, Doug.
Okay, so if you would tell us a little bit about your background in HPC.
Sure. So for the last 3 years, I've been part of Dell Technologies in the HPC and AI Innovation Lab. For the 12 years before that, I was at the Texas Advanced Computing Center, working on some of the largest academic supercomputers in the world.
Okay, so you last spoke with us in November at the SC conference. That's when you spoke with the late Rich Bruckner interviewed you before the conference. You two talked about a fascinating topic: brain decoding using neural networks to, in some way, read minds. What does that mean? And can you give us an update on the work you're doing?
Sure. So this is a collaborative project that we've been doing in collaboration with McGill University, the Montreal Neurological Institute, and Intel, looking at using deep learning to decode functional MRI activation maps. Now, what normally happens is when a patient takes a functional MRI, what they're trying to do is figure out what regions of the brain are activated by having the patient perform a task like remember what they had for breakfast or move their fingers or their toes while in the imaging machine so that they can see which regions of the brain light up, which regions activate. And what we're trying to do is take that image of an activated brain and infer using a neural network what the patient was being asked to do. So we're reverse mapping that fMRI image, turning it from the image back into the command that they were given when they were performing the test.
Okay. So as I understand it, the ultimate goal of this research is to build better deep learning neural networks with the ultimate goal of moving AI from narrow AI to taking on more than a single task at a time. Do I have that right? And what's the key to taking that next step?
Well, that's right. So the ultimate goal would be to have some form of general intelligence. Of course, we're not there yet. We're still focused on narrow intelligence. But what we want to do is be able to use knowledge that we've gathered about the human brain in order to help inform the way we design artificial neural networks. And one of the things that we're looking for is the ability for the human brain to context switch its neurons. So the brain doesn't use individual regions for specific tasks. It reuses all of the neurons in the brain for multiple functions. And there's a process called context switching. And we're hoping to be able to replicate the context switching capability of biological neurons and artificial neurons by studying how biological neurons are actually functioning.
So how does it work when you're doing research like that, where you're really taking us into the unknown? Do you sort of see incremental progress, or do things tend to kind of suddenly converge and you make a big leap forward?
So when you're doing exploratory research like this, where you're really not sure what the outcome's going to be, you tend to have to uh, take things as they come. You end up with lots of incremental progress or maybe going down kind of a wrong turn. Uh, what we're working on with McGill and the Montreal Neurological Institute is work that they've already kind of done the exploratory legwork on. So they're beginning the implementation process and the data collection process. They're now working with patients back in Canada, having them sit in MRI machines and take fMRI images while doing more complex tasks. So instead of just wiggling your fingers or your toes, they're having them play video games in order to properly map the different regions of the brain that are working in concert with one another to solve that particular problem. They have visual processing, they have auditory processing from the sound of the video game, they have to do decision making and motor control all at the same time. So they're at this stage in the research process where they've already have a very good plan. They're doing this data collection. They want to be able to do this computational step in order to see what kind of knowledge we can tease out of those functional MRI images once the more complex task of playing the video game is being done.
Okay, interesting. So you mentioned data collection. Can you quantify the amount of data involved here, and also uh, profile, if you would, the hardware resources you're drawing on for this project?
So for the first phase of the project, where we're looking at single tasks, there's several terabytes of data being collected in the form of these fMRI volumes, which are between 30 and 60 gigabytes each. And there's about 60 to 70,000 samples of those 3D volumes. So the objects themselves are too large to fit inside of a single GPU's memory space. And usually when you're doing deep neural network training, you need at least one entire data object to fit inside the system's memory at one time. So what we're doing is actually using Intel CPUs to do the training, because we have access to the system memory, which is significantly larger. So we did all of the training for these models on the Zenith cluster in the Dell Technologies HPC and AI Innovation Lab, which is a completely Intel Xeon-based system based on the Dell EMC PowerEdge C6420 server.
Okay, so I know you take part in the Dell Technologies HPC community meetings. How do you view the value in cross-discipline groups like this and in support of your AI work at Dell?
So these cross-disciplinary studies are extremely important, especially in the artificial intelligence space, where everything we're doing is kind of state-of-the-art work. This is a lot of ground that hasn't been trod before. So the ability to work with researchers in the field from various different disciplines and backgrounds is really important, because while in certain domains like high-performance computing, we understand the workloads very well, in artificial intelligence, we really have no understanding of what the de facto standard workload is going to be. So when customers and researchers have problems like this, where they don't know what algorithm they need to use, how scalable that algorithm is going to be, or what infrastructure to run it on, we're happy to explore those things along with the customer, help them determine what algorithm works best, how to scale those algorithms, and what infrastructure is ultimately going to work best for the problem they need to solve.
Okay. Well, great, Luke. So we'll be looking hopefully for milestone announcements on this research work you're doing with McGill and other work that you do. And thanks so much for spending time with us today.
Well, thanks so much for having me on, Doug. I appreciate it.
Okay, great.